Thank you very much, Sid. Hello, everyone. Thank you very much for the invitation to participate in BQIT. It's always a great pleasure to join this wonderful conference. So today I'm going to be talking about demonstrating quantum advantage with practical photonic systems. Let's go and see a little bit what type of quantum advantage I have in mind when I talk about this. So I'm going to be talking, the general context is, of course, quantum communication networks. And the idea here, the main goal will be, in my talk, will be to cases, specific examples where it has been possible to demonstrate a provable quantum advantage in security and efficiency for communication and cryptographic tasks in a quantum network scenario. So here I'm going to be considering essentially photonic quantum networks. So I'm not going to be discussing about the network nodes like memories and a few qubit processors, etc. But obviously these are proof of principle applications, and the goal is to deploy them in future quantum networks. And towards the end of my talk, I'm also going to show how it's possible to extend this communication framework to show even an advantage in a computational time perspective that we have shown recently. As you know, I think most of you know that the main application of one of the most advanced applications in quantum networks is, of course, the one that is used for securing the network links, which is quantum key distribution, which provides a future-proof and information theoretic secure solution to the key agreement problem. I am not actually going to be talking about this today. As Sid mentioned, we have a lot of work in our lab in Paris in this direction on QKD systems based on continuous variables and entanglement-based QKD as well, and including feasibility studies with satellite links. So we're addressing challenges regarding the integration of such systems in the photonic network and cryptographic integration, working towards advanced nodes. And I would invite you to see what we're doing in this direction in the workshop at the end of the week, in the next generation quantum networking workshop. Today, I would like to focus more on other cryptographic tasks and other communication tasks, and how we can demonstrate in practice a quantum advantage. So it's important to understand that there is a big and rich world in security and communication beyond key distribution. There we have other security models which offer many more functionalities, and the communication networks offer a beautiful framework for demonstrating quantum advantage in this case. Here I show you a few examples of protocols that you may have heard of that are extremely important building blocks of communications in networks. Often they're territory of computer scientists, so it's important to make them compatible with physical experiments. So this takes a while. Typically, the protocols, when we approach them, they use inaccessible resources. They are vulnerable to imperfections. So it's important to adapt them to such conditions. And then, of course, when we claim a quantum advantage, it's extremely important to perform the correct comparisons with equivalent classical resources. And I have found that this is a very crucial point in such implementations. So I'm going to start with showing you a couple of examples that we have done of such cryptographic tasks, and then move on to more communication efficiency field. So first of all, we worked on quantum coin flipping. This is one of the main primitives, cryptographic primitives, that is, for example, used in distributed computing. And we performed a theoretical analysis based on the first protocol that was completely not robust to experimental imperfections, to allow, for instance, for honest aborts, okay, in case that the quantum coin flipping protocol implementation is not perfect, we have to necessarily allow the participants to abort, even if they are honest, to take care of these imperfections. So we did this experiment, and we showed a few years ago with discrete variable QKD-like system, a quantum advantage from metropolitan area distances. This was for a strong coin flipping protocol. There is a subtlety between the strong and the weak quantum coin flipping, where the weak offers the possibility for one of the two parties to have a preference, a bias towards one of the coin flips. And this is crucial actually for applications. It's a lot more subtle to actually implement it in practice. This is why it has taken us longer. And we now have a concrete protocol based on single photon entanglement, and it's currently in a process implementation in our lab. So this is an example of a protocol that needed specific adaptations to be able to demonstrate the quantum advantage over reasonable distances. Another protocol that is interesting is the quantum money, which was actually the original protocol that was used by Wissner based on uncertainty principle before even BB84. And it was considered for a long time very hard to implement for exactly the same reasons. It of course needs quantum memory. It needed a bouncing of quantum states from the bank to the client and vendor with non-demolition measurements. So this was extremely complicated. So we have built upon previous work to propose protocols that can only work with classical verification. So basically, the bank prepares the quantum money states, gives them to the client in the form of the qubit states. Then they are immediately measured by the vendor, okay, who is supposed to be trusted in this particular implementation, the trusted terminal, so the security guarantee is against a dishonest client. And then the whole security is based on challenge questions that the measurement needs to answer with respect to what the quantum states that the bank had prepared. So the implementation here as well was based on a let's say QKD type protocol, but with more subtleties. In particular, the average photon number per pulse had to be a lot lower than in typical implementations. And so you come up with a secure region of operation where you can show that the probability of answering the bank challenge correctly is a function of several experimental parameters, and you can show that it's strictly bigger than what you would have in a classical scenario. And so that's why this is how you can have a rigorous proof of unforgeability for this type of quantum money protocols. And for this, it's essential to adapt the security proof to the real implementations that are not using real single photon states, but weak coherent states. Okay, so this is extremely important in the same way that we're doing for QKD. And now currently we're working on operating this with a real quantum memory to store the credit card states and retrieve them to be able to perform the money transaction. So I think this is going to be a neat example of how we can use quantum memories actually for something that is not for a cryptographic protocol, which is quite uncommon. A final cryptographic protocol that I wanted to mention was the one of multipartite entanglement, which was actually started with a collaboration with our Bristol friends a few years ago. So we used the GSET multipartite states, which is one of the most valuable and precious resource of future quantum networks. And the idea here was to prove that you can have dishonest parties among the participants in a network who want to perform a distributed task, and they need to make sure that the state, despite the presence of dishonest parties, remains the one that they want, so close to a perfect GZ state. So this was not easy. This is a difficult protocol. It requires very high performance resources in the state, in the sense of high fidelity. And we could even show the result, but with quite small loss tolerance. And this, for me, is a good example of the gap that there is between physicists that do quantum states, okay, multi-part entangled states, and actual protocol implementations, where it is actually a lot harder than we think to satisfy the constraints of the actual quantum communication network protocols. So we have theoretically applied this to anonymous message transmission, where the verification phase guarantees anonymity. We have also studied the composability of this framework from a security point of view, and we're currently working in the implementation of this anonymous message transmission protocol based on this verification in our lab. In the second half of my talk, I would like to focus now on quantum advantage in communication resources. So this is also very much inspired by computer science type of protocols. Here we have parties that communicate in a network they receive inputs, and their goal is to output a function of these inputs with minimum communication. So this is the field of communication complexity. And the idea here, it has applications in data structure, secure computation, VLSI design, lots of this type of applications. And the idea, again, is not anymore about security, but is the amount of communication that the distant parties require to jointly perform this distributed task. So a protocol that has been studied carefully by computer scientists is so-called hidden matching. So what does it mean? So basically, in hidden matching, Alice and Bob, as you said, receive inputs. And in particular, Alice receives input in the form of a string of bits, and Bob needs, from the message he receives from Alice, needs to be able to, he receives this collection of pairings, of matchings that you see on the right, for example, an example of a four set, and he needs to output the bit, the parity bit between two elements of one of the pairings within each matching. So it is a very conceptual protocol for us physicists, but what is really important, it was that it has been shown that there is an exponential advantage that is gained by using quantum resources instead of classical resources for this type of protocol. So we have log n in quantum versus square root n, where n is the size of the input message in classical communication. And of course, I should note that this is a one-way communication. Okay, so this is quite important. So actually, demonstrating this gap has been considered really, really hard. It was shown that to do this, you need this type of very high-dimensional input states, it's so-called fingerprints. And even if we assume that the low size fingerprints of the type that you see here can be built, for actually demonstrating quantum advantage in practice in the presence of imperfection, it's a lot harder, and you need a large input size. So you will need single photon states across many modes or a big number of entangled qubits. So when this n is on the order of hundreds or thousands, so you understand that this is completely out of reach of present experiments. So what we did to approach this issue is that we used this coherent state mapping that was proposed recently, where these fingerprint states are mapped to a time series of n time modes. Okay, we have a total mean photon number of alpha square spread across n time modes. So we have string of coherent states, and actually this can be rigorously shown that they span a Hilbert space that is equivalent to the one that we need for our protocol demonstration. So we showed for this one, the exponential gap that we just saw is preserved not for the communication time, because obviously you see here that instead of sending very complicated entangled states, we send time series, okay, very long time series of coherent states. So we don't gain in communication time in this particular example, but we gain in transmitted information, how much information is included in the input of these pulses. So this mapping allows us to do the implementation involving only coherent states, linear optic circuits, and single photon detection. It was used for fingerprinting, but we still show that it is still not possible to use it for this communication complexity protocol. The demonstration would still be quite overwhelming, with we show that it will need lots of loops with big strings of pulses that becomes quickly impractical for large n. So what we did is that we devised a new protocol that we call sampling matching, that you see here, where now we have, the question is phrased differently. We have an input from Alice, and the question that we want to ask is, what is the transmitted information that Bob needs to output? What is the transmitted information that is needed for Bob to output the correct parity from a uniform matching set? So this is extremely important, with a given success probability that is characterized by this value delta. Okay, so this is a different way of framing this, and actually just to mix a little bit, to match topics. It was very much inspired by work that has happened in round-robin differential phase-shift quantum key distribution. So I'm saying this for the experts here in the field that know everything about all the QKD protocols. So we performed this analysis. We saw that the gap still holds in that case, and then we moved on to perform an experimental confirmation of this quantum advantage with a relatively simple setup. So you see here in this green part of the graph that it was possible. So we want our experimental poise to be on the right of this green curve, and this shows that that we can beat the best classical protocol. But we showed at the time, so that was in 2018, that the lower dark counts were required to beat the lower bound, which is the official, from a computer science point of view, the classical lower bound overall that can be achieved for any protocol. And now, very, very recently, just I'm not showing the result here because it's very preliminary, we have actually crossed that line too by using very state-of-the-art superconducting detectors. Very final point, we applied this, as I promised. I wanted to show you, before concluding, the very last example of how this can be applied to a computational problem. So for us, it was very interesting to apply this prover-verifier interactive setting with technology that is basically currently available for a useful computational problem. And this was given by a protocol that was proposed by Scott Aronson some time ago, where he had shown that we can verify hard problems when we have access to limited information. This is important to clarify. I'm not going to go through the detail, unfortunately, of the problem here. It's extremely interesting, but we don't have time, and it's quite complicated. So it takes months for computer science and physics to speak the same language to actually understand this. But what we did, we essentially translated this verification, this limited knowledge verification problem, to our sampling matching scheme, and we managed like this to perform the experimental validation. So you can see here on the left the gap between the correctness and the soundness of the verification procedure, which shows you what is the average photon number that you have to apply. And then we went on, we applied this average photon number, and then we showed that the gap, the quantum advantage, was verified with the detection pattern on our single photon detector. So we showed that this verification test can be done in a few seconds, while it would take much longer time in a classical computer, with the only assumption that it takes exponential time for a quantum computer to solve and a classical computer to solve the NP complete problem. So this is an example of how a quantum advantage can be used for useful applications. So we're thinking, for example, of server-client type secure computing, where, for example, the prover, so Merlin here, the prover, is, for example, a quantum computer that can perform this type of computation and find the solutions, or has access to solutions to NP-complete problem. And then Arthur is a simple client, photonic client, and we wish Merlin to perform this calculation, but Merlin does not want to reveal all the solution because of proprietary issues, for example. So this is a type of application that one can think in a client server-client type of cloud computing, and in all other applications where we have access to limited knowledge proofs. So with this, I would like to conclude. I would like to thank very much the collaborators, especially for this last part of the topics that I covered. I hope I have convinced you that there is many interesting things to do with current and near-term quantum technologies for showing an advantage for truly useful tasks. And I believe that these types of experiments give real insights for more complex applications and push photonic technology to better and better performance, while demonstrating now, without waiting for a full-scale quantum internet or a full-scale quantum computer, that there are many interesting things to do with quantum photonic technologies. Thank you very much.